Hello friends! In this video, we are going to explain dynamic programming. This is part of a series that is dedicated to explain algorithms in the easiest and the most visual way. And I say we because I'm not alone. I have Phanto, who helps me doing that. First of all, this is a new channel, and I need your opinion to see whether I should continue what I'm doing or not. So, if you like what you hear, I would appreciate if you hit the like button and subscribe to the channel if you want to be in touch in the future. That would mean a lot to me. Now, what is dynamic programming? Dynamic programming is a technique that is used to solve programming problems.
But does this mean I can apply dynamic programming to solve any problem?
Of course not. To solve a problem with dynamic programming, the problem should have the following. It should have optimal substructure and also overlapping subproblems. Optimal substructure means the optimal solution to the problem is the combination of optimal solutions to subproblems of that problem. This means if the problem can be divided into smaller problems and you managed to find the optimal solution to each of these problems, you will find the solution to the bigger problem. For example, if you have got a few series A, B, C, and D, and you are trying to find the shortest path between A and D. If I tell you that the solution is ABD, this means that there is no shorter path than ABD to reach from A to D. This means that the shortest path between A and B is AB, because if there was a shorter path from A to B than AB, we would have taken it already in the solution. So, here in calculating the shortest path between A and D, we calculated the shortest path between every city in between as well, and that is the optimal substructure. Dynamic programming can be used to calculate shortest path problems, although we will go through shortest path problems in another video. The second condition here is overlapping subproblems, which means that if you go through and you start to solve these subproblems, you will find yourself solving some of these subproblems over and over again.
That was not clear to me. How am I going to solve the same problems over and over again?
This will make more sense when we give a real example. Let's use the Fibonacci series as an example. We have explained the recursive solution of the Fibonacci series in a video before. If you like to check it out, you will find a link to it in the info box. A Fibonacci series is a series of numbers that look like this. The first two numbers in the series are 0 and 1. Then, starting from the third number in the series, each number is calculated as the sum of the previous two numbers. So 1 is the sum of 0 plus 1, 2 is the sum of 1 plus 1, 3 is the sum of 2 plus 1, and so on. Fibonacci series is a perfect candidate of a dynamic programming solution.
But why?
First, because it satisfies the optimal substructure condition. To calculate each number in the series, you will sum up the previous numbers together, and to calculate those, you will sum up the previous numbers together and so on. So the solution of the problem depends on the solution of subproblems. Second, did you notice the overlapping here? For example, let's index the numbers in the series starting from 0. So to get the solution of the series at index 5, we need to calculate the number at index 4 and the number at index 3 and sum them up together. But to calculate the number at index 4, we need to calculate the number at index 3 and the one at index 2 and sum them together. Do you see the overlapping? This overlapping can be hard to recognize at first, but it will become easier to spot the more you get exposed to dynamic programming problems. You will be able to sense the pattern in the problem and say, aha, this is a dynamic programming problem. Let's code the solution of this problem. The most natural solution that comes to mind is the recursive solution. Again, we explained that in detail in a video in the info box, so check it out if you want more details about the recursive solution. Let's create a function that takes n as a parameter. N is an integer that represents the index for which we want to calculate the Fibonacci series. We know that the Fibonacci of 0 is 0, so let's reflect that via an if condition. Fibonacci of 1 is also 1. Let's add an if condition for that. Otherwise, the solution should be the Fibonacci of the previous two numbers summed up together. Now let's try that. Let's get the Fibonacci of 5. That's 5. Correct. Now let's get the Fibonacci of 7. That's 13. Also correct. Now let's get the Fibonacci of 50. Oh, it is taking so much time to calculate. Phanto, can you guess why?
Of course I can. That's because of the overlapping problem you mentioned. I think we are calculating certain Fibonacci's multiple times, right?
Absolutely right. Let's trace the solution on paper. Let's say we need to calculate Fibonacci of 4. Fibonacci of 4 is Fibonacci 3 plus Fibonacci 2. Fibonacci 3 is Fibonacci of 2 plus Fibonacci 1. Fibonacci of 2 is Fibonacci of 1 plus Fibonacci 0. Fibonacci of 1 is 1, Fibonacci of 0 is 0. Here is the overlapping problem that we have.
But what if we save the solution of Fibonacci 2 somewhere and use it when we need it?
Oh, Phanto, I don't know why you are here. You already know everything. That's very correct. We can save the solutions to Fibonacci's that we already calculated in an array and check in that array if we have the Fibonacci number before we calculate it. Let's try that. I will add here an array called cache. This array will have n plus 1 integers. We will pass that array to the function. Then check if cache of n exists. This means that we already calculated the number before. Then we return it right away. Here we need to store the result of n in the cache array. And that's it. Now let's try to get Fibonacci of 50. Oh, that's so fast. Obviously, the caching approach improved the performance significantly. This approach that we use now is called memoization or top-down approach.
Okay, we are saving the results in order not to recalculate them. So memoization makes sense, but where is the top-down in that?
It is top-down because we started from the end result, the bigger problem, and then divided that into smaller problems.
I'm still not convinced.
Okay, let me first introduce you to the other approach, and this will make it more understandable. Sometimes you just understand the concept by understanding the opposite of it, you know.
Alright.
The other dynamic programming approach is called tabulation or bottom-up approach. With that approach, you start from the bottom and gradually build your way towards the solution. Let's have a look again at the Fibonacci series. If we know that the first two numbers in the series are 0 and 1, now to get the Fibonacci of 2, which is the third number here, it is the sum of the previous two numbers. If we start a loop from here on and store the calculations in an array, as we did it with the memoization, this will be the tabulation solution. Let's write that down. We create our fib function. First, we create an array which has a length of n plus 1. We know that the Fibonacci of 0 is 0 and the Fibonacci of 1 is 1. So we set them in the array. Then we loop starting from 2 and start calculating the missing Fibonacci up until the number that we are interested in, which is n. And then we return the Fibonacci of n from the array. That's tabulation. Now let's try that. Let's get the Fibonacci of 5. That's 5. Correct. Depending on your preference, you might find tabulation even simpler than using recursion, and I tend to find it simpler, actually.
Okay, everything is fine. But why we created an array with size of n plus 1?
Because array indices start at 0, and we want to store the result up until the number n. If you have an array of length of n, the index of the last element in that array will be n minus 1. But since we want to store the result of n, we need one more element to the array. Now, let's calculate the time and space complexity. Let's start by the recursive variation first. As always, please pause the video and try to calculate the time and space complexity yourself first. Alright, actually, it is easy to calculate the complexity in here. In each call to the Fibonacci function, we call the Fibonacci function 2 times. And in each of these calls, we call the Fibonacci function 2 times, and so on. This means 2 times 2 times 2, and so on. How many times are we going to do that?
I think we will do that n times. Because once we reach 0 or 1, we will just return the solution which we already know. Either 0 or 1.
So, complexity is O of 2 to the power n. Just make it a rule. Time complexity of a recursive function is the number of times you recurse to the power how many times you are doing that. Space complexity here is 1, because we don't use any storage. Now the memoization approach. Here we check in the cache array before we start the calculations. This means we are not going to repeat ourselves at all. Each Fibonacci is calculated only one time. This will leave us with the time complexity of O of n. Space complexity here is O of n as well, because we store n numbers of results. The same for tabulation approach. We have a time complexity of O of n and space complexity also of O of n.
No, we store n plus 1 results. The array has a length of n plus 1, so we should have a space complexity of O n plus 1.
Yes, Phanto, but with complexity we ignore constants. It doesn't really matter if we are going to do one more iteration at the end. In computing complexity, we only care about the significant parts. We are going to explain how to calculate complexity in another video. I hope that you now understand the concept of dynamic programming. We are going to explain more dynamic programming problems in the future, so make sure to subscribe to the channel and click the bell icon in order not to miss on that. If you like the video, please hit the like button, and if you have any questions, please write them down in the comments. We answer all comments. Thank you for watching.